Good morning. Hello and welcome to this month's Power Hour. My name is Urbano and I'll be your host for today's session. Today's presenter is Romulan, an application engineer and instructor here at NxRev. She'll be covering unlocking the power of master modeling. For those new to our Power Hours, the format we will follow starts with 45-minute demonstration and explanation, followed by a 15-minute question and answer session at the end. If you have any questions, please submit them through this meeting's chat box. I will collect them as we go, and that way we can cover them during the Q&A session at the end. Before we get started, let's review our upcoming Power Hour schedule. So there on your screen, I have a table showing the topics that are coming up. Today we've got unlocking the power of master modeling. Next month in August, building curvature continuous surfaces will be the topic. We've got several others: measuring and collaborating with Creo View, making data available with Navigate, troubleshooting regeneration issues, and we'll wrap things up for this year with participating in workflows. That's that's a Windchill related topic. So they will all follow the similar format, and with few exceptions, they'll be on Thursdays at 10 a.m. If you want to sign up for any of the subsequent topics, please visit our website. I'll go ahead and give you a short demo. Go to our website, you'll see this. In the training drop-down list, there's a Power Hour top subject, and if you go ahead and select it, it'll take you to a page where you can actually go in and register for all the topics or individual ones, and they'll send you a GoToMeeting link. Okay, so I do want to remind everyone that recordings of these sessions will be made available through our Jira ticketing system for customers on our extended support program. If you want to know more about that extended support program, please send a message over to sales@nxrev.com. So without further ado, I will go ahead and make Romulan the presenter and let her take it away.
All right, thank you very much, Urbano, for that introduction. So welcome everyone to NxRev's Power Hour sessions of 2019. My name is Romulan Mirador, and we'll be looking at unlocking the power of master modeling, also known as top-down design. So once again, my name is Romulan, and I have been with NxRev for 2 years now as an application engineer and instructor. Before I joined the team, I've worked as a high school engineering teacher where I taught students how to use Inventor. In college, I worked on a small satellite project that you see at the bottom of the screen, in which we used SolidWorks to create the CAD. And now I work primarily in Creo, offering technical support and training at the NxRev office. On our agenda for today, we'll be going over master modeling. First of all, what is master modeling? And then we'll go over the process, as well as the best practices. And at the very end, we'll go over a demonstration. So what is master modeling? Well, let's actually begin by looking at the traditional design process, or also known as a bottom-up approach. In the bottom-up approach, you create individual components independent of the assembly and then place them into sub-assemblies or the top-level assembly. As you assemble these components, you may notice that some components do not fit each other properly. For example, pins are not aligning with their proper holes. Later on, you will have to correct and adjust those components if that's necessary. If significant design changes occur that affect many of the components, such as changing the overall width of the design, you must manually identify and modify each affected component. As the assembly grows in complexity, correcting the inconsistencies do become very difficult and time-consuming. So let's enter master modeling, or top-down design. Now, in the top-down approach, critical design information is actually placed in a single high-level location, and then communicated to the lower level levels, which are components of the assembly structure. Parts can be placed into the respective assemblies at any point, and parent-child relationships are actually linked to a central master model. Now, if significant design changes do occur, changes can be updated at the higher level, and those changes will propagate accordingly into the lower levels. Okay? This helps with easier management and organization of complex designs, and also gives us a predictable change in our designs. All right. Now, there is a process for the top-down design, and we'll go over those steps. So the first step is to create a layout. The second one is to create an assembly structure. Third, you'll create a design framework. Fourth, you'll share critical design information. And then last, you'll start creating those design models. So the very first step in the top-down design process happens actually before you even start the CAD. You start the design by actually sitting with your team so that you can discuss and document any of the design intent or the critical design information that you want for the product. Okay? Documentation can contain 2D conceptual sketches of the design or specific design criteria and specifications. So for example, you can have dimensions that define critical size and mounting locations for components, critical design parameters, or mathematical relations using parameters and dimensions so that you can convey design constraints. Now, this step may take some time, but it is a critical step so that in order for you to create a more robust design, as well as save time down the line, especially when there are those significant design changes. Your next step in the top-down process is to create your assembly structure. Now, this is almost like a list of your sub-assemblies and components placed into the assembly. And then you can also organize and get your hierarchy of all of your components. This is an excellent way to organize your product's assembly structure at this point. And at this stage, you're not going to be concerned with defining the component geometry just yet. So we're just going to be creating these empty parts. You'll also start placing them at the default constraint. And later on, if you need to change those constraints, you can do so at another point. Okay. What's also useful at this step is that you can add any bulk items. So bulk items are components that do not require any design geometry. And this can be things like glue or oil. The next step in the design process is to create your design framework. Now, you can actually use this by using skeletons, or they're also known as master models in your assembly. A skeleton itself is a unique part file that generally contains zero mass geometry. So these could be things like datums or surfaces. And these are actually excluded from math calculations and interference checks. Now, when you create a skeleton, they are placed as the first component in a new assembly, and it contains the critical design information for the product. When you do create the lower level components, they actually reference this skeleton. Okay? And if changes are made to the skeleton, those changes are updated in the components that reference them. So for example, we do have basically the assembly structure. One of them is the bottom-up approach. The other one is going to be the top-down design. At the left here, we have our bottom-up approach. So we start off with, let's say, component A, and we have components B, C, and D, and all of them are actually referencing component A. Okay. Now, if we do start deleting some of our components, so for example, if I delete component B, we also notice that component C references component B. So if I delete component B, component C will also be deleted. And since component C is deleted, component D is also referencing component C. Once that gets deleted, component D will also be deleted as well. Okay. If you use the master modeling technique, all of your components are actually referencing the skeleton. So there's no need to worry about deleting one of your components and having it delete any other components down the line. So this does help to eliminate or reduce unnecessary parent-child relationships. Now, skeletons can also be used to define space requirements, critical component dimensions, and mounting locations, or critical interfaces between components, or also motions between components of the assembly. So here we have an example of using space claims or space requirements in the skeleton. We're allocating space in our printer feed that we have here. And then all of these components are actually created by using enclosed quilts. And those enclosed quilts are actually defining the volume of those sub-assemblies or the component itself. Now, these shapes can be very simple, just like these boxes that we see here. And later on, when you pass on this information to the designer, they can start populating and including all of those aesthetically pleasing features. Okay. Another example of a skeleton is a skeleton that contains critical interfaces. So here we have an engine assembly, and here we have actually surfaces in this skeleton to define interfaces between the components within this engine assembly. Okay. Any change to the interfaces of the skeleton can update actually the corresponding components. All of these are surfaces that are basically shared common areas between components of the assembly. The last kind of skeleton that you can use is a motion assembly. So you can have a simple 2D sketch that has some mathematical relations to help simulate the motion in the assemblies. In this case, we have a landing gear example where it's just simulated by simple 2D sketches with dimensions, as well as some parameters and some mathematical equations or relations. Now that you've designed the framework, it's actually time to start sharing your design information. All right. When you are sharing your design information, you can either push information or pull information from the top level to the lower levels of your assembly structure. When you push design information, you can use what is called the publish geometry feature. The publish geometry feature contains a collection of geometry references from the component or skeleton model in which the feature is created. Okay. This allows you to package or basically predetermine the geometry to be referenced by a copy geometry feature. This also helps reduce possibility of other designers selecting incorrect geometry when you're trying to use copy geometry features for designing your components. Pulling design information can include copy geometry itself, so you can copy references that are stored in the published geometry features onto your components. It's useful for concurrent design in a concurrent design environment. And it's used to communicate all those geometric references, information, and user-defined parameters to and from parts, skeleton models, and assemblies. This also enables you to reduce amount of data in session, so you don't have to open up the entire reference source model. Right. Other ways you can pull information is by using a shrink wrap feature, which is an excellent way to capture geometry from entire assembly structures. And you can also do inheritance features, which is an effective tool for downstream processes such as manufacturing. Now, once you start sharing your information to those lower levels of the components, your designers can actually start creating the models. So for example, I have this printer again, where I can share the enclosed volume of the top paper feed to the first engineer, and he or she can start populating the top paper feed with all of the features and components that he needs. Okay. Moving forward, let's actually talk about some of the best practices when you are creating or when you are working with your top-down design process. So one of the best practices is to actually create, when you are creating your skeleton features, make sure that they're in the skeleton model. We do want to avoid creating assembly level skeleton features. Any static information that you have in your skeleton you want to place that into your skeleton if possible. Try to consider proper naming convention for your skeletons as well as critical features in your models. And you want to make sure to actually document and establish those top-down design best practices for your company, so that your company can follow and enforce these down the line. If you do create published geometry features, we do suggest adding those to the footer. And you can also enforce proper use of the top-down design process by using the following configuration options. So in this case, you're going to help with the references tied to the skeleton model itself. Okay. Now with that, we'll actually get into the demonstration. So the first step, let me actually show you what will start creating pieces of. We have our fan assembly that we would like to create, called our Vortex 1200 fan. And we're going to use the top-down design process to create this fan. Now, the very first step before actually getting into the CAD is to create the layout. Now, this step is once again an important step to discuss with your team so that all design intent or critical design information is determined and documented. So once again, documentation can include conceptual designs, design requirements, or critical size dimensions, mounting locations, or design constraints. So here's an example of a concept design or conceptual sketch of the fan, as well as the specifications that it does that we are trying to include in the fan design. So that's the first thing that you will want to do before you start creating your models. Once this is all finished, you can start going into Creo to start creating the product. So let's actually start off with opening Creo. Your next step after creating your layout is to start creating your assembly structure. Now, once again, we're going to create basically just a list of all of your sub-assemblies and your components in a new assembly. So let's actually start off with creating a new file, a new assembly here, and let's call this our Vortex 1200 fan. Okay. I do want to make sure I'm using my correct start parts or start assemblies. So I'm going to navigate to my start parts that I will use. Say OK here. All right. So we're just focusing on populating our assembly structure. So I do want to make sure that I include the skeleton model. So to include the skeleton model, we'll actually use this create tool. And you do have the skeleton model type to use. Okay. You can give this a proper name. Sometimes it will automatically populate with a underscore SKEL or skel at the very end of the file name. All right. And when you are creating, you can just copy from existing. Typically, I like to copy from existing because we're trying to use templates, our start templates, to keep this all robust in general. Let's say OK here. Now, the skeleton, when you do add that in, it will be the very first component in the assembly at the very top, and that's where we want to make sure it stays during your design process. All right. Now, I do want to populate my model trees even further. I do want to add in the fan unit assembly, as well as the base unit itself. So I have two sub-assemblies that we're going to create. So once again, I'll start creating a sub-assembly, one for the fan unit. All right, let's say OK here. Once again, I do want to make sure I'm using the correct start assemblies. All right. And when it asks you to place them, we can typically just use the default constraint. So here I'm just right-clicking on the screen and adding it to the default constraint. All right. It just so happens that there is basically a database for the company's fans that we're going to reuse. So in this case, for the fan unit itself, I want to include the drivetrain in the assembly. So let me just activate this part here and include the drivetrain assembly. This is something that we're just going to reuse and already has all that other information that's standard across the company. All right. We also want to make sure we include let's say the drive arm and the housing. So let's create a couple of other components here. So I have the drive arm. Let's pick up our start parts. And once again, put this at our default constraint. So you'll notice that I'm just starting to populate my model tree. If at any time I need to start reordering them, I can easily reorder them in the model tree so I can define the hierarchy of the assembly structure. Now, eventually we'll get to a point where we have our completed assembly structure. Let me actually create one more sub-assembly, which is going to be our base unit. All right. Start assembly. Add this in. The default constraint. All right. So eventually we'll start creating all of these parts in your subassembly as well. Let me actually start with creating a part called the main base. Let's see here, start part. All right. All right. Now, eventually, when you start adding in all of your components, you'll have your completed structure tree. And if you need to add in any bulk items like glue or oil, you could do this at this point as well. Now, let's actually start moving forward by starting to create our framework. And when we are creating our framework, we're actually going to use the skeleton. So as best practice, to avoid creating skeleton features at the assembly level, let's actually open up the skeleton model itself. So let's open this up into its own separate window. Okay. Now for the skeleton model, we include any of the critical design information, and that could be things like dimensions of critical size and mounting locations. And so for this product, we're going to just start off doing some basic sketches to determine some of those critical size dimensions too. So let's actually say that one of our datums, actually, we do want that to represent the ground. Okay. So the top plane is actually going to represent the ground. I do want to create a curve, or basically a sketch, that's going to determine the length of the post for the base. So let's actually start by creating this here, a sketch. Do this post sketch right over here. And this post, we have specified that this is going to be at a dimension of 3.5. All right. So that's one of our critical size information that we need. We also want to include a sketch of the base of the base itself for the fan. So I'm going to include that on. Let me actually get this here and call out our base sketch from our sketcher palette here. So I already have a base that's sketched out, so I'm going to add this in. And let's just relocate this here and scale it back 1:1. And let's say OK. All right. And let's finish out that sketch. So here we have some critical size dimensions that we are including in the skeleton. You can also start including datums for either mounting locations, or if you're trying to incorporate motion for your skeletons as well. So for example, if I wanted to create another reference, a tilting plane reference for motion of the fan itself, I can do so. Let me actually start creating a plane that's going to be at the top of this vertex, as well as parallel to this ground instead. All right. I can have another axis that we'll create that's going to be at the intersection actually of our plane that we just created, as well as the right plane. Let me actually do that here. Just create an axis at this intersection. So that axis is going to be our tilting axis for the fan. I can continue forward in creating more planes. So another tilt angle plane, for example, to show you the tilt of the fan itself. But eventually, once you start populating all of this information in your skeleton feature, you can have something that looks similar to this. So let me actually open this up. So for the sake of time, I actually included the skeleton feature. Let me actually put this here. The skeleton model that has all of those mounting locations, any of those critical size dimensions already included in. Now, it's not limited to just sketches and datum references. You can also include items like space claims, or once again, motion, or critical interfaces. So let's actually do an example where I'm going to start creating some space claims for our fan itself. And we're going to actually take a look at the base unit first. So if I wanted to create some space claim information with the base itself, I'm doing this all within the skeleton model still. Now let's actually extrude this out. And when you are creating your skeleton models, once again, these are typically going to contain zero mass geometry. So instead of extruding it out as a solid, I'm just going to extrude this out as a surface. I'm just going to go ahead and cap the ends as well. So here, I basically created just a really simple extrusion so that I can denote where the space for the base is going to be contained within. All right. I can also include space claim information for, let's say, the drivetrain assembly. Now, the drivetrain assembly itself, let me actually say, has already been created. So once again, we're actually going to reuse the geometry that our company has because we don't want to have to recreate the wheel, right? So let's open up a model. I'm actually using the shrink wrap feature to basically share some design information. And let's actually open up that model and search for our drive assembly. All right. And then where I do want to place this, I actually have a coordinate systems that we set up for mounting locations. So one of them actually is going to be the coordinate system for the drivetrain itself, which happens to be the DT main. And we do want to pick a coordinate system on the skeleton model. And that happens to be called skeleton main here. So I'll pick those up and press OK. And now we have included a shrink wrap model of our drivetrain in the skeleton model itself. So this is another space claim information that you can share to the skeleton model. All right. And then we can do another space claim, maybe for the cage or for the blades of the fan. So let's actually start by sketching on this surface. And what I want to do actually is get our interface here. Oops, let me actually get out of this. Our interface surface to face the top so that we have a clearer picture. All right. So let's create a space claim that's going to basically show us the diameter of where the blades are going to be. So the specification gives us 11 for that cage or that blade or the blades itself. And we want it at a depth of about 1.375. Okay. Once again, zero mass geometry. We want to use zero mass geometry for our skeleton. So I'm just going to make this as a surface so that we have basically a space claim for the cage or the blades themselves. All right. Now, those are some examples of how you can introduce some space claims into your skeleton model. You actually get this ready here. Okay. Your next step is basically trying to share information to, let's say, to the individual components themselves. So let me open up another example here. Eventually, you'll get to a point where you start having all of your space claim information, your motion in your skeletons, or even critical interfaces in your assemblies. So for example, I had the space claims that we created for the blades. We have the base itself, and there's also some surfaces here that we see, which are basically critical interfaces where two components actually share this common area. Okay, so I did a copy geometry of that specific surface so that we know that this is going to be a shared surface. And I'm actually going to use this information so that we can create our actual parts. Now, for this part, we want to start creating basically the main base. So once again, I don't want to create any assembly level features. I'm going to actually open up this part on its own. And when you are sharing information, you can either push or pull. In this case, I'm going to pull design information from the skeleton model itself. And to do that, I'll use the copy geometry feature. So clicking on copy geometry, let's actually make sure we pick up the correct reference model, which is going to be our skeleton model. Okay. Stay open. All right. And I'm just going to let it be set at the default constraint for now. I'm going to turn off the published geometry for now, and we're actually going to start selecting basically references from the skeleton model to use. So since I'm working on the base model itself, I want certain information, including this critical interface. All right. I do want to get the height of the post as well as the base geometry. So I'll include all of those in. And there is an axis that we want to keep to help with our tilt of our fan itself. So let me actually turn that on. I do want to make sure I populate that and grab the tilt axis as well. All right. Once I say OK here, in our model tree, we have basically our external copy geometry feature. And I'll just show you what it will see. And we can actually use all of these references to start building out our models. So here I've just shared all of that critical design information that I would need in order to create this model. Maybe since I am still working on that base, I would want to get the surfaces, the space claim basically of the base itself too. So I'll just create another copy geometry feature where I'm going to grab that space claim for the base itself and make sure I just put this at the default. All right, let's turn off my published geometry. And I'll just grab, I'm going to use my seed and boundary selection here so I can grab all of these surfaces at once. Also control select this, and then middle mouse button to finish this out. So now I also have the space claim information for the base. Now that you've shared your information, you can start creating all of the solid features. Now I'm the engineer who's designed to create the base itself. So I'm going to use all of these references to create our solid features. Now, one of them is, let's actually say, we would like to create basically the post, starting off with the post of our base. So let's grab this here. We're going to extrude on the front plane. And I'm using basically that critical design information that we needed. We're going to use that as our references. So I'm going to actually project this. Let's say I need that outer diameter there. All right, project that onto my sketch and start creating our post. So let's start. Now I already have all of this information where this post is supposed to be about, I believe, 3.5 units tall. All right, so all of that's already created. Oh, let me actually make sure I delete some segments there. Go. And let's make this metric and about one unit deep there. I do need to create some cuts here as well. So we have another component that's supposed to come in and share basically the critical interface right in the middle here. So let me create another extruded cut. And let me actually project and clip my model here. So next, accept this. Now I do want to create basically a line, a horizontal line here, and delete some segments. So I have another cut that's going to go through this post. All right, so we have all of this that's going to just go through all of the other half. And I also want to make sure I have a hole so that we have these components being held together. So let's create the center hole there. Remove material and flip it to the other side, going through all like so. And then since I am the base, the engineer creating the base, you can continue forward with creating all of your finishing designs. So for example, if I wanted to include a round at this post, I can go ahead and create that full round at the post just like so. All right. So that's some information that you can do once you have that skeleton information. You have this shared design surface or critical design surface interface, so that when I go into my actual part or my actual assembly, where that post is, we'll see that the surface that we were using is also shared basically with the support arm as well. All right. Now, because it's shared with that support arm, let's say that we have some design change. For example, the post itself needs to be a little bit thicker. That's one of the design changes that the company has and wants to enforce there. Now, we'll see that if we do make this thicker, it probably also need to make the support arm just as thick as well. But we don't want to actually go into typically in the bottom up approach, we would need to go back into all of these components to make those changes for each part. Now, if you're using the skeleton model or the top-down design approach, and you have that interface, that critical interface already set up in your skeleton model, you can actually just go into your skeleton model. Let's say, open this up. All right. And let's take a look. Once again, we have that critical interface, that shared common area there. And if I make changes to this, let's say this needs to be a little bit thicker here, or a little bit larger there, and regenerate. We can always go back in. Let me go back to our model here and regenerate from here as well. All right, and you'll notice that not only does it update this part for the base, but it also updated the support arm as well. All right, so instead of going to multiple places to make those or adjust those changes, you can just do it all through the skeleton itself, and it will propagate throughout the assembly, saving you a lot more time itself. All right. So that does conclude the demonstration for the master modeling technique. We did go over the what top-down design is, the process and the steps to create your top-down design models, and then some of the best practices as well. So now we'll actually go ahead and open this up for questions. So if anyone has any questions, Urbano?